Hello and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg. Remember that we are powered by Research Luxembourg and recording in the studios of RTL City. Our guest today is Dr. Emmanuel Defay, who is the head of the nanotechnology unit at LIST, so Luxembourg Institute of Science and Technology. Prior to coming to Luxembourg, he worked at the CAA Leti in Grenoble in France. His research interest is mostly on piezoelectric thin films and devices, but also on the electrocaloric effect occurring in ceramics and polymers. Emmanuel, thank you very much for coming today.
My pleasure. Hello.
Okay, so we're going to talk first about nanotechnologies. I was thinking about it today a little bit. You might know or not, but in order to record this podcast, I need to bring the micro SD card. And it's a pain for me because it's so small. And I'm thinking like, oh God, I'm going to lose it. And that's definitely not as small as the materials you're working on, right?
Indeed.
So nanotechnology, what are we talking about? How small is it and why is it so small?
Yeah, that's a good question that we often have. So, I mean, it's a very generic word. It's a dimension, right? So it's a length. So if you take, typically we are less than 2 meters, then that's the meter range that we have. So if we divide by, let's say, 1,000, so we reach 1 millimeter. So 1 millimeter starts to be a bit tricky then to also see. Then if we go 1,000 less than this, so we divide by 1,000. So this is the micron range. So micron, to give a flavor of these on our body. So you take your hair and the diameter of one hair is typically 50 micron. So here, when we talk about nanotechnology, it means that on the devices, or not necessarily the devices, but the materials we are working on, we have at least one length of the thing we are working on, which is less than 1 micron. So meaning that we enter into the nanotechnology world. So that's the door is below 1 micron. So below 1/50th of the diameter of the hair. So then in terms of thing that we are working on, so it can be nano powder, so which is something that is not necessarily well appreciated by the majority, but it gives the possibility to prepare a lot of interesting things related.
Why not? Because you can blow it away because it's a powder.
Yes, there were still a lot of discussions, probably more 10 or 15 years ago, because some people were afraid of nanotechnologies per se, because indeed, so you can breathe it, so it's probably related to pollution or to pollutants, which is here not the case, but it's the active part of it that can be extremely good for medicine typically. So we still have one group and one unit at least working on it specifically, so it's not in my unit anymore. So that's we call nanomaterials. In my unit, nanotechnology, so we focus mostly on films that we deposit. So a film is probably the closest example is the films that we have on our glasses. So most of us have glasses, and at some point,
at least we have, here, 100% of guests and people working.
Our glasses are made of plastic or glass, and on the top of this lens, most of the time we deposit something. So we have very, very thin layers that are in this nanometer range. So it can be 10, 100 nanometer in thickness, and those layers have specific properties, optical properties. So anti-refractive coating, for instance, to avoid the blue refraction of our computers, for instance, or then that we can see through. I don't know if you remember 20 years ago, or perhaps even before. So I remember my dad, so he had glasses where you could really literally see yourself in the glasses. So the reflection was much more. Now we know all the technology to make a smart coating that avoid this kind of reflection. And then, so that's why we call it anti-refraction coating. It's opportunity also for the glass makers to add function, but to charge also us a bit more on this. But this is real good technology with plenty of other possibilities. So this is one kind of something I can relate to everyday life for everyone. But there are plenty of things. So an object that is also very, that takes a lot of advantage of all these nanotechnologies, our mobile phones, where there are plenty of things that rely on nanotechnology, or let's say nano devices, that wouldn't be possible without these technologies. So and here the best example would be certainly all the chips, the microelectronic chips that we have. So all the let's say the brains that we have in our computer or mobile phones that are made of extremely small devices, so transistors. And to do it, so we need specific tools that we have in LIST. And yes, well, that's pretty much the kind of definition I could tell about nanotechnologies.
So you mentioned as an example glasses, because the whole idea is that those films are transparent.
Mm-hmm.
Right? So you would not print something that is actually noticeable in any way. And anyway, it's nanotechnology, so you can't see it, can you? You changes the characteristics of the material.
Yes, so you can change here the optical properties with some layers that are transparent, but it's not necessarily transparent. So there are other technologies. You want it to be opaque, so we can deposit also metals that are not transparent. So if you put a few nanometers, so they can be transparent or semi-transparent. But most of the time we use metals because we want them to be conductive. So if they are conductive, they are thick enough, and then they are not transparent anymore. Though there are also possibilities to make transparent conductors, which is one of the specialties of one group in my unit, depending on the devices we want to make. So I give another example. So beyond the transistors or then the chips. So this is how to functionalize a glass, not necessarily for optical functions, but to make them tactile. So there's a project we had some years ago, and that now we are pursuing, trying to find new solutions. What we try to do is to make the screen of your mobile phone sensitive, or the other way around. You want to be able to sense, to feel something when you touch your screen. So that's already the case with the vibration that we all know on our mobile phones. But there are other technologies, and the deposition of some specific layers on the top of the glass sheet or the cover glass that we have on our mobile phone is another possibility. So we can make different functions. So here the idea, and that will make a link with my research more directly, we try then to create vibration on the cover glass. How do we do it? We use another smart material that we call piezoelectric materials that can induce this vibration. How do they do it? So those piezoelectric materials are materials that can move or change their shape if you apply an electric field, a voltage. So to make it very simple, you take a battery, you apply the battery on the material. So, and to apply this battery on the material, you need wires, and you need something conductive. So that's why I was mentioning metals that we can use. And when the voltage is applied to the material, there's a strain, there's a deformation induced into the material. And then if you do it right, so meaning that you are not using a battery, but something that can modulate this voltage, then you can also modulate the amplitude of the deformation on the glass. And this is something you can feel with your finger. And on the top of that, you can make it completely transparent. To do it, you need transparent piezoelectric materials, but also transparent electrodes. So it's all, very tricky, of course, but it's extremely exciting. And on the top of that, so it works. So that we are very happy with it, with this solution.
You can confirm that. And I think you can also find on the web a video where you're kind of demonstrating at least an early stage developed idea where you can touch and see. So I guess when people participated in Tech Day, a couple of years ago, they could touch it themselves and see.
Absolutely, yeah.
But why do you need that? I understand the science behind it and all that, but did you find a special need where you thought, this would make sense to do? Well, vibrations are there. Why do I need to know, I don't know, if I'm buying something that this is how it feels, that it's a rock, if I'm looking at a rock?
Yeah. There are two things that were thought of regarding this application. There are probably much more. The first one is to emulate the feeling of touch. So meaning that, for instance, if you want to buy something, I don't know, probably, it's all disputable in terms of real interest for the future of humankind, but you could potentially emulate something you want to buy. So I don't know, some fabric, some specific thing. So you could then feel already directly on your mobile phone. So meaning that makes an experience which is closer to reality without having to move. So that's one thing. Another possibility that is also more advanced is to give the opportunity for blind people to then see something directly on the mobile phone, so that you can emulate braille. I don't know if in English that's the right term, but braille language, so that you can also feel it with your fingers. So then, and this possibility would be possible with this technology of piezoelectric materials, but not with the vibration we have, because it's not very subtle. So you can feel the vibration, but not something that you can, if you take your finger and you go, you move back and forth. You rub it back and forth. Here, this technology gives you the opportunity to feel a kind of, a small bump, and this bump can be moved. So depending on the vibration that you excite, and this one can be of interest for blind people.
If you print it on the screen of the mobile, and then many people have now some kind of a cover, right? So like those, glass, would it still work?
Excellent question. So that we used to work with a company in France on these, and this is one of the tricky questions. So how to be sure that the vibration is large enough, whatever happens, so that big fingers, small fingers, cold fingers, cover glass or something under cover glass, so that to be sure that it's extremely tricky, and then pushing the technology to the next step is another challenge indeed.
So we went to another step, but I want to go back a little bit and understand, why do you want to put these materials on glass? Why glass and not something else?
Well, glass is nice because it's transparent. That's first thing. Second, now we all have glasses or functional glass in our pocket, just in the studio, so that there's plenty. And the more we go, the more we want to touch this glass. So meaning that there are plenty of opportunities. So here I focused on the touch feeling, but there are obviously, we see through the glass, we can also change the color of glass. So there are other plenty of possibilities to do things on glass. So that's why glass is so interesting. So there are, I would say, 3 main substrate, we call them substrate, on which we can work. So silicon, which is still the mainstream, so where we make all the chips for microelectronics. So microprocessors are made of these microcontrollers. Then glass for what I just mentioned, and also polymers that are more and more used. So there are also some screens that are made of polymers. They would be cheaper. We have also glasses made of polymers. So this is the other possibility also to make those substrate functional. And the kind of trend is to use all these nanotechnologies to functionalize all the substrate to experience more probably more data or more possibilities to monitor your health, for instance, or give you ads when you are in town, for instance. So that's the idea. So there's a lot of activity around these ideas.
As usual, a lot of possibilities, and you need to choose something, and probably that's difficult sometimes. Like, what do we focus on now?
Yes,
it's a bit of betting here,
yes,
for sure. Okay, so I understand you take this film and you print it. And I also understood that you use inkjet printers for that, but not the classic ones. The glass would break if it just went through an inkjet printer.
Yes, indeed.
Sorry, probably a stupid thing, but when you start reading it, you're like, okay, so do you adapt the printer, or how does it work? Like, if I enter your lab and you're just printing some film, what would I see?
Yeah, essentially the same as a printer we have at home. It's just a bit bigger. So it's typically something, 1 meter by 1 meter by 2 meters in height, but it's essentially the same. So we have cartridges on which you put some ink. Just that the ink, we prepare the ink ourselves. So we have also a chemical lab in List where we prepare then all the specific things we want to print.
And the ink is transparent?
Not necessarily. So it's really chemical. So depending on the solvent we use. So, but this ink is full of things that we don't want to keep in the end. So it's chemical, organic chemicals most of the time. And we want to get rid of them, and to get rid of the one after we print it. A bit the same as our ink in the printer at home, just that here, we don't see exactly the color of the ink, but it's probably not exactly the color that we have eventually on paper, because there's a solvent and we get rid of the solvent. Just that here the solvent we use just evaporates when after we print. And this is exactly the same as what we do, just that we have to help a bit more the solvent to escape. So we have several heating treatments, which is also a very big part of the technology we develop. What are the best treatments that we can use? They have to be compatible. I was mentioning before the different substrates that we use. So silicon that can withstand high temperatures, so up to 1,000 degrees. Then glass, it's much more tricky. So the ones that we have on our mobile phones can be 400, 500 degrees, and polymers it's 100 degrees typically, a bit more, but just to give a range. So meaning that we have to adapt also the heating treatment. We have to change the inks that we use depending on the function we want and depending on the thermal constraints that we have. So a lot of technical stuff that in the end make all the difference, prepare something functional and unusual.
So is it also one of the reasons why silicon is so popular? Is that because it's so good with heating, like you can easily remove the solvent when you're printing something on it?
Silicon is a It's a big story. So I think silicon has a lot of advantages. So first, it's extremely, what's the word? So there's a lot of silicon in the world. So 25% of the Earth's crust is made of silicon, or silica, but there's silicon in there. So it's abundant. Second, it is a semiconductor. So meaning that we can adjust how good conductor it is or how good insulator it is, depending on different, what we call doping. So we add some
You
specific...
call it doping, really?
Yes, doping,
Okay.
yes. So we add some specific materials, and that are very often what we call rare earth. So
Okay, so I would, sorry to interrupt, I would just say that's the legal doping, right? In that
well,
case. Or not?
I don't know. But this is also, you probably saw that there are a lot of discussions about materials that we need for now. So lithium is one of them.
True.
But there are also rare earths that I mentioned, so that are mostly in China, or mostly developed or refined in China. And with all these political, difficulties, so it makes all countries thinking a bit differently. So, but we need those materials to make our chips. So that's also one of the reasons. So we need to find a way to get access to those materials. We don't need much, but we need some of them in a crucial way. And then another very specific thing with silicon is that it has a very nice and very reliable oxide. So we can oxide silicon, and it makes also the entire technology very, very practical. So so a lot of technical reasons as well. But all these, it started in the 50s. So, but now we can refine silicon in a really perfect way, and we work on. I cannot show you here, but it's essentially a kind of a disc of silicon that can be up to 30 centimeter in diameter, extremely thin, so 1 millimeter typically. And we make all the steps in these silicon wafers. We call them wafers because it looks like a bit of wafer. And then the technology reached such a level of refinement that, it's just amazing to see. So we were mentioning nanotechnologies in thickness, but now the size of one single transistor is a few nanometer in width, which makes hundreds of billions of transistors in one wafer. So, yes, it's just very difficult to just imagine how small it is if you are not on the topic itself. But it's, all this explains the power of our mobile phones and, all the technologies related to communications and all that. So it's all related to silicon technologies.
So I got you talking about silicon, but you're not really, looking at it that much. It's glass more.
Yes,
so,
it's more glass and even more so. It's more on the functional materials. So here we talked about glass, we talked about inkjet printing. So those things are typical things that we worked on in the lab. But there are other applications, if I can put it this way, that are related to the materials that we deposit. All those materials that we are studying, at least in my group of research, come mostly from one single family that we call perovskite. It's a bit, bizarre name.
Yes,
that comes
it is.
From one famous people who discovered the structure some more than 100 years ago. And that we use now for very different applications. So the idea or the way we run our research is that we are experts on this family of materials, and we try to find different applications. So it's probably a good way. There are perhaps other ways to be impactful, but if you want to make a difference in research, it's probably good to be an expert in your topic by definition. And being an expert on everything is just impossible. So here, the way we see it is to be expert on the material and then try to deploy it through different applications, because that's also one of the things we do, at least trying to work also not only on the pure scientific interest of the topic, but also trying to push it, or to, I don't know if we push or pull, but towards the application.
Okay, yes. That's why also when I was preparing, I was thinking a lot about the applications, because it's true that with LIST you kind of have that, at least a demonstrator where you can see, then depends whether you get a partnership or not, but you definitely have that kind of more tangible and understandable part of your research. But when we were also talking before today, you kind of mentioned, but now I specialize more, and you mentioned energy, right? This is kind of what you focus on. But then materials, you just said, and the energy, what's the link here?
Yeah. So thank you for the excellent question. So energy is really the motto of all these materials coming from the perovskite family. Why? Because those materials are, to make it short, we call them smart, which is, doesn't really tell what it means. But more specifically, they have the power to transform one form of energy in another form of energy. So I was mentioning piezoelectric materials. Those materials can transform mechanical energy into electricity. So you press them, meaning that you put some mechanical energy in there, or vibration or deformation. And the material, when it moves, so creates electrical charges. But you can do the other way around. You can apply an electric field to the material, and the material will deform. So meaning you can see it in two different directions. So this is one way of using those materials. So here I mentioned actuators, so things that can move the screen of your mobile phone. Another topic we are working on, which is related to energy, is energy harvesting. So this is kind of popular, and it has been popular for now, 20 years to some extent. And now it becomes more real. The idea is to get rid of batteries. So we had, for instance, during the last Researchers' Day, so we had a booth dedicated to it with one colleague of mine. And the idea here is to try to find sources of energy that would be wasted somewhere, or that you wouldn't really pay attention to, but trying then to then collect this energy, store it in a battery that would be a capacitor, and then use it for a function. So this trend is extremely also interesting, because we are now more and more trying to get a lot of sensors everywhere. So in our cars, in our gas sensors in rooms, things that could also be helpful in your mobile phone for your health. So something that could detect your heartbeat, for instance, or if you have some specific chemicals that are traces of even cancer or from your breath. So there are plenty of things that can be done, and for this you need sensors, and the sensors are very small. So we mentioned here nanotechnologies. And you have to supply those sensors. So you need energy. Whatever you do, you need energy. So now that I think that one thing that probably came with the crisis we are living now is that now people are much more aware of the need for energy, what energy means. And it's true for our heating, but it's true also for everything. So piezoelectric materials, we have also a big effort on this energy harvesting thing. But there are also other members of this family, perovskites, who can link two other sorts of energy. We are always trying to link it with electricity, because that's easier and that's more practical for sensors. And also, when it comes to energy, the future will be electrical. So that this one, we know that hydrogen is also another very big trend, and we are working in my unit on hydrogen as well. But my personal research is more on the electrical side. And then we have materials that can link heat or temperature change with electricity. So, and the same as before. So we can use them either, so you apply or you change the temperature of the material, it will create charges, it will create voltage, and you can make energy harvesting. Or you can do the other way around.
And these are the pyroelectric materials?
This is pyroelectric materials, yes, well done.
I passed the test.
You passed the test.
Hooray.
And then
Before we go on, actually talking of passing the test, I was just listening to you so attentively and so many interesting subjects and all that. I realized, it's quite long that we're talking, and we haven't asked the pub quiz question that normally goes in the beginning of the podcast, but I hope listeners will forgive us for that. And also it is related to what we were discussing just right now. So energy in general. So if I can ask you to ask the question, and then listeners remember the answer will be only at the end. And that's for sure the end of the podcast.
The question I wanted to ask is indeed related to energy, and I'd like to know how much energy we dedicate to heating and cooling. So meaning overall, so in the entire energy that the humankind is using, so what is the percentage of energy that we dedicate to heating and cooling?
On Earth.
On Earth.
We're not counting, space station or something.
Not space station, okay. Which is probably very little compared to what we use. I think this is a very important question. Of
course, and very interesting one as well. Remember, answer at the end. But now we can go back to the pyroelectric, I still remember, materials, what you mentioned. And also this is related, if I got it right, at a moment I was reading the news and it was like you were popping up this prestigious publication here and a prestigious publication there. I have to mention, because I guess for a layperson, if you give some of the names of the journals people don't know, but you are definitely related to two publications of two scientific journals that are pretty known even by lay people, which is Science and Nature,
Yes.
right?
Yep.
And that last one was in Nature, wasn't it?
Absolutely.
Yes. So the pyroelectric in the sense of using waste energy.
So it could be waste energy indeed, but could be also energy coming from the sun. So this is one of the things we are thinking about now. So I mean, there are obviously a lot of complications or difficult things to put in place. But if we and to talk about the paper we wrote, the one published in Nature, we didn't put the finger on something that was unknown. We somehow just revisited something that was already touched a bit in the 60s. But now we have much better materials. We have also a better understanding of the way those materials work. And we know they kind of secret. And the secret of those materials is what we call a phase transition. So meaning that you can somehow enhance very much the properties of those materials, whatever it is. So this coupling property I was mentioning, so the door or the size of the door giving you the opportunity to go from one sort of energy to another one. So this one can be enhanced very much by the phase transition. Phase transition is the arrangement of the atoms into the material itself. And the fact that on those materials, you can control the apparition of the phase transition with the electric field. So that's the kind of... I don't know how to express it better than this, but when you apply the field, you can go from one, and you can apply the field, you can change the temperature, you can then go from one phase to another, and this way then decouple or enhance very much the properties that you are looking at. So here in the case of the pyroelectric harvester, because here we called it harvester, so we try to convert heat variation or temperature variation into electricity. And our discovery is that it's really the amount of energy we could harvest is way higher than what was done in the past. And so that's one point. Second point is that the efficiency, what we call efficiency, meaning how much energy you can collect from what is available. So there's always a maximum size for this door that I was mentioning. So meaning there's one part that you cannot convert. But we observed also that the efficiency can be extremely large in certain conditions and very close to this phase transition. And the third interesting point is that devices that we used, the material was put in some devices that are to some extent pretty well known. So meaning that if we could find the right materials, and we are not there yet, but I wouldn't say on the verge, but really looking for these, and there are very good signs that we will find a way to find the right materials. We could then scale up the fabrication of these devices in a pretty easy way because it has been done with other materials.
And what I also understood, that a bit of background knowledge, because I talked to one of your colleagues, is that one of the applications we could talk of is using these temperature changes to create energy when, for example, I don't know, in rovers on the moon or not.
Yes. So that there are possibilities also to collect energy in space. So it could be also, for those materials, what we need is a change in temperature. It has to change versus time. So it has to be cold, hot alternatively, which is a bit annoying. That's why we can
Why annoying?
Annoying in the sense that there's a competing technology that we call thermoelectrics or Peltier effect, where in this case, so you don't need a variation in time. You need a gradient of temperature. So meaning that you need to put the material in a space where the temperature is not the same everywhere in space, not in time. And to some extent, it's easier to use, but it's not as efficient. So that's why this technology on modified pyroelectric materials has an interest.
And what kind of temperature variation do we actually need to have significant energy production?
So here, the higher the better, of course. But then there are technical complications because you don't want to lose this energy through leakage. So there's always, when you go too high in temperature, so then the devices start to leak. So that's one difficulty. You want your material also to be able to be active on all the regions. So I was mentioning this phase transition that occurs at specific temperature. So that's another difficulty. And an extra difficulty to this is that as we are using what we call a thermodynamic machine, we are limited in terms of efficiency by some rules in physics that we call the Carnot law, discovered then by Carnot a long time ago, where that essentially says that the efficiency is larger when the variation of temperature is larger. So that's why it would be much more efficient to have extremely large variation of temperature. So to give an example here with our plants, so be it nuclear plants or coal plants, even though we try to avoid this, but all the plants that are used to create electricity, typical variation of temperature, or the highest temperature is typically 500 degrees. And then the other one is the one that we can get access with rivers, so which is around room temperature. And this large variation of temperature then enables to increase this potential efficiency. Here we are not exactly in the same case, but we are limited by the same law, and that's why ceramics, so these perovskites are ceramics, are extremely interesting because they can potentially survive very large variation of temperatures.
When we were talking about piezoelectric materials, you mentioned that you also looked at the reverse situation. What about pyro? Are you trying to also create temperature variations?
Yeah, so it was actually the beginning of this story about the two papers that you mentioned that are strongly linked together. So one is on the pyroelectric energy harvesting, so trying to then create electricity from the sun. So I'm not sure I explained very well this one, but it can be wasted energy, but it can be also something that could be ideally a solar panel, modified, but that's also the ambition and the possibility. And indeed, so as I said, so we started with the other part of the story that when we studied those materials, we started to look at the counterpart of the pyroelectric effect, which is called electrocaloric. So then electrical part and caloric that suggests that we are changing the temperature of the material. And the beauty of it is that you can heat the material, but you can also decrease its temperature. Same in a cycle here, meaning that potentially you can make fridges. So, and this is what we try to do. Just to rewind a bit, and why did we study it? So it just happened with an opportunity I had before coming here in Luxembourg. So I spent 2 years in Cambridge, University of Cambridge, as a visitor. So I was still employed by CEA. But I was there to study this effect that I found super interesting and super exciting. So with in the team of Professor Neil Matter, and I was really amazed with it. So we started to find different materials, and then we built at the time a key partnership with a Japanese company, which is called Murata, and I am still working with them today. And then we started to look at the best materials that we could imagine to have or to display this electrocaloric effect. And little by little, so we studied the material, then we said, okay, now that we have the material, could we try to make a kind of prototype, which is more things that we do here in Luxembourg compared to the characterization that they initially did in Cambridge. And then we found that indeed, so we build something which is really good, and that good that, well, actually we could beat a record that was lasting for, I think, 35 years or 30 years, which is this variation of temperature. So, and I think before what we showed, so nobody thought that electrocaloric materials could be a real competitor for potential fridges. But here we somehow surpassed a psychological threshold, which was 10 degrees, so we reached 13 degrees. And now we are doing even more. And then that's the time we made it in science. So it was during the COVID time. So it was really something that cheered us up, as you can imagine. And also somehow put list on the map when it comes to these electrocaloric and then pyroelectric materials. So meaning that we have a very strong portfolio of projects related to these energy concerns.
And I actually now remember that this is how I read about you the first time, because when I was starting the podcasting, I was just informing about science news in Luxembourg, and I did inform about fridges and research as well. So I'm going to share the link to the show notes when I was starting, and you were starting also in the materials, let's say starting, because I guess that took some time until you got to the publication, yes. But still, more or less, I'll share that in the show notes. But another thing I was thinking of, I just, looking, we've already mentioned glasses today a lot, right? So you have glasses, I have glasses. Just seeing these materials, do you actually, when you do the research, do you have to see them? Are you using microscopes? How does it work? Because of course, you just can't sit and say, okay, now something is happening. Well, you can't see them at all, right? Without special microscopy.
Yes. So, it's true for small things. as you mentioned. So there are things we cannot see with our bare eyes. So our eyes can see, down to probably a few microns. So it's still possible. Below, it's impossible, and physically, it's not possible. So we have indeed microscopes to see it, and we have now a super transmission electron microscope, so that can see really the atoms. So that's one possibility. But here, also on the topic I was mentioning related to heat and electricity, so that's the same. You want to put your finger if you want to feel the vibration, but when you apply, 100 or 200 volts, so you don't want to put your finger, so you can feel it. But yes, we have also tools to look at the different electrical properties. So same as what you would have at home for a multimeter, for instance, if you want to see if you have 220 volts on your socket. But also when it comes to the variation of temperature, so we have also specific cameras able to see the temperature changes. We have all sorts of tools that are, providing data, and then we analyze the data, and this is true whatever size we use. So the small things, but also the bigger things that are for the fridges. So we have things that are much bigger than. So it's to some extent nanotechnology, because we are studying the atoms. The devices are big enough that you can take in your hands. So you see them to some extent.
To some extent. Yeah. Okay. So you mentioned piezoelectric, pyroelectric. Is there anything more in that collection of materials that you look at?
Yeah, there's a lot of different coupling that are also available. So here I mentioned specifically to look at the different coupling that we can imagine. So you have to look at the different sources of energy. So there's then electricity. So most of the time we try to link it with it because it's easier to generate data and to characterize the materials. Then mechanical parts, so the mechanical energy, so vibration, deformation, the magnetic field as well. So here, and we don't study it very much. So I have a colleague of mine working more specifically on this coupling with the magnetic field and electricity. Another interesting field that I came across rather recently, where you can also couple it with chemicals. So meaning you can couple electricity, chemistry, and heat. I was asked to also comment on a paper that was published recently in Science, where people called this effect ionocaloric, which are materials where you can change the temperature very much by adding some chemicals, and you can control the amount of chemicals you add into this system with electricity. Meaning that there are a lot of things that can be done, a lot of different coupling that can be imagined.
And reversal as well. And
reversal. So because all of them are or most of them are thermodynamic effect. And if it's thermodynamic, it means that essentially you can think it in both ways.
Okay, so a lot to discuss still and discover and whatever. Another publication. Yes, I will not keep you too long then, so you can go and, although I don't know. I've talked to quite a few researchers that basically work all the time, so would assume that, weekends are probably also spent on research once in a while.
Limited, but indeed, so it's this job is really about passion. So, and when you have passion, so it's difficult just to cut, and which is not always easy to manage. But yes, it's really endless.
Yes, and for me, it's also about passion, and I could continue talking for another 3 hours. But I don't know whether the listeners would stay with us, but for sure they are staying because we need to solve the pub quiz question as well. So if I can ask you once again, if you could ask the question and then give us the answer.
So the question was about the total energy that we spend on heating and cooling on Earth. So all this related to the activity of humans. And then the answer is 50%. So meaning that it comprises heating our buildings, cooling our buildings in summer and then in the countries where it's very hot, but also all the processes related to industry. For instance, steel industry, so that we know well here in Luxembourg. Also all the things related to concrete fabrication that also needs a lot of energy. So all sorts of energy you can think of, all thermal treatments that you need. So this is all comprised in there. And it represents by far the biggest amount of energy that we need to just, have the life we have today. I think it's important for people to realize this. Why? Because if we want to make it, so in Europe, so we know that by 2050 we need to reach to reduce the global warming, we need zero emission, and to do it, so the biggest chunk of source of CO2 is this one. the one dedicated to heating, meaning that we have to insulate our houses. We need our industrial companies to try to reduce the amount of energy they use, so finding new processes. And if I relate it, for instance, to the CO2 emitted by all the planes that are everywhere, so this one everyone knows, and there are a lot. I don't want to play the game of those companies, but I think it's important to see the difference, that if you say, okay, I won't take the plane anymore, okay, but here you are playing on the 3% of CO2 emission, 3% only, if I may, only if we compare it to the production of CO2 induced by the heating, which is 50%. So somehow nothing to be compared. And this is also a strong motivation for our research, that we want to find new ways for cooling that are more efficient. We want to find new ways for creating electricity from heat, because there's a lot of opportunities. You were mentioning waste heat. There are possibilities, there are certainly technologies to be developed, and this is indeed so a very strong motivation for us, because we are attacking the big part of the source of CO2.
Of course. And when we talk about energy, we also need to mention that, because that's also the tricky part. Let's say I had a couple of months ago already, Dr. Robin White, also from LIST. Yep. We were talking about, of course, hydrogen, what else with him. And he was also mentioning that kind of a trap we can end up with, because, when we are finding new sources of energy, new ways of producing it, we still have to kind of go all the way back on how much, do we have to do in order to actually get to the moment when we are producing the energy. Yep. So the methods you're talking about, what kind of a decrease of CO2 we're talking in comparison to the, classic energy production? Like, for example, the harvesting. There will be no CO2, I guess, for producing the harvester. And that's it.
Well, I mean, here the harvesting is probably not the right word if we want to really replace all these sources of energy and make them completely green. So it's really the production itself that needs to be addressed. So meaning that in this case, so it's really trying to find efficiency is really the key. So when we want to produce electricity, we always talk about efficiency. So if we take photovoltaics, which is one of the best solution, perhaps the best solution ever for the moment, so it's around 20%. We can now there are works that are better, but if you buy something, so it'll be typically 20%. So it means that if you had 1 kilowatt coming from the sun, at maximum you can produce 200 watts. So this is this number that is interesting. So meaning that if you have a new technology that appears, obviously, so there's the cost of production that matters a lot. But the main point is really how efficient this can be. So can you make something which is better than photovoltaics? So this is typically the kind of threshold that any technology has to go through to make a difference. So that's the first thing I would say about this.
Okay, so you first look at that and then you try to figure out the rest.
If it makes sense. So obviously you have to see whether then the industrialization of your solution makes sense or not. But I mean, before, if you cannot tickle a bit, the best contenders, so you have very little chance to do it. But we have to try. Okay,
well, your research definitely sounds like a lot of fun. We had tickling today, we had waffles and, doping and, and what was it? I also liked something you made a comment about annoying, the annoying differences between temperatures. So, annoying, I was just already imagining that, it's annoying because as you're making the variation of temperatures, all the researchers have to put the jackets and take them off because there is a variation. It's just my imagination going wild. I'm very sorry about that. But I hope that all our listeners enjoyed the episode as much as I did, because it was really interesting to kind of get a small glimpse into your world and see where you're going. And hopefully, you will just come back at a certain moment to tell us more about next materials and next applications. But first of all, thank you so much for coming today.
Thank you very much for having listened to me.
This is it for today. As usual, don't forget to subscribe, to follow us, to check what we're writing about on Twitter, LinkedIn, Instagram, that will not be writing, but posting different things. And just write to us if you have some suggestions for guests or just comments about the episode. Remember, this was Silax, and my name is Hanna Siemaszko.